Okay. Good evening, everyone. My name is Chandan Kumar Gupta. I am a research scholar in IIT Patna. I am your PMRF TA for Probability and Statistics course. This course is offered by Professor Somesh Kumar. He is a professor in IIT Kharagpur. Okay. Okay. Now, can anyone confirm? Is my screen visible?
Yes, sir.
Okay, thank you. Okay. Okay. I think everyone already seen the lectures provided by NPTEL. This course is mainly introductory course for probability and statistics theory. Okay. These are the course layout for this course, and it is a 12-week course actually. And every week there is a 2 hours TA session. You people are requested to please watch videos before come here. Okay, so we can discuss about the numericals or problems on the topics that are discussed in the lecture. Okay, these are the layout of the course. Like in week 1, we are going to discuss about the sets, collections, rings, sigma fields, and monotone classes, random experiment. From there, actually, we will start. From there, actually, we will start probability part. Okay. Then events, types of events, definition of probability. There are different types of probability definition and the properties of probability functions. In week 2, we are discussing about the continuous conditional probability, independence of events, and the problem related to independence and conditional probabilities. In week 2, we have also discussed about the random variables and then the probability distribution of random variables. Then after that, we will discuss about moments and characteristics function of these distribution functions. And in week 3 also, discrete distributions, some special kind of discrete distributions are taught or teaching. Okay. In week 4, Poisson process, Poisson distribution is also a kind of discrete distribution, and the Poisson process are in week 4. And then in week 4, we will also discuss about the continuous distribution functions, like normal distribution function and uniform distribution function, maybe log normal distribution function, and so on. And in 6th week, we will discuss about the random variables, joint distribution, independence of moments, and these are actually the outlines of the course. It is just in week 7, we will discuss about bivariate random distribution function, normal, and the properties of normal bivariate normal distributions, the transformation of random variables. From week 8 on, we will discuss about the exact sampling distribution, that is chi-square, T and F distribution. These are also known as small sampling distribution, actually. Then after that, we will discuss about the descriptive statistics, which is like the distribution of data, how we evaluate the distribution of this type of data. Okay, and then we will continue the descriptive statistics in week 9, and after that we will discuss about the theory of estimation, which comes in the statistical inference part. Okay, in this we will in this section actually we will discuss about the estimation methods like least square methods, method of moments estimator, maximum likelihood estimation, some goodness, some properties of estimation like unbiased, consistency, sufficiency, efficiency, etc. Okay, and in the successive weeks, we will discuss about the uniformly minimum variance and bias estimator, and most of the examples are done on that topic. Okay, and in 11th week, we will discuss about the hypothesis testing. There are two type of error in hypothesis testing, the Neyman-Pearson lemma, and the application of that. And in week 12 or in last week, we will discuss about the testing of normal means, testing of normal variance or proportion. These are actually the course outline that we will cover in the successive 12 weeks. Okay. Since it is our first class, how many of, okay, there are 10 people are there. So everyone watch the video, na?
Yes, sir. We have watched.
Okay, you have watched. And I think we should just introduce each other. Okay. Who's, what's your name? I think it's not totally visible in my screen. Can anyone? Okay. So, Arya, can you introduce yourself? It's just introductory session actually, na?
Yes, sir, I'm here.
Yes, yes. And where are you from?
I am from Karkala, Nitte.
Okay.
I am a
And
PhD scholar in the mathematics department in the college at MIT, Nitte.
okay, nice. Okay,
Thank you,
and
sir.
why have you chosen this course?
Actually, for us PhD, we want a coursework, so that I have chosen this, sir.
Okay, okay, okay. Thank you, thank you. And
Thank you, sir.
Deepak, Deepak. Okay, and then Modin. Okay, anyone?
Yeah, hi, sir. Good evening.
Yeah, yeah. Good evening, good evening. So,
Sir, myself, Gauss. I'm pursuing a part-time PhD from Yanapoya, and it is a this course why I have chosen it is a part of my course curriculum. So I have to at least give a certificate of clearing this exam and all. And the
okay,
statistics where I am doing my related work on my PhD topic on entirely biased to the statistical part where though I am from library science background, so I'm contributing some oncology research where the statistics has been taken care with South Asian studies. So that's the reason I need to know how the probability and statistics will take care in my thesis, and that will lead to understand thoroughly in giving a brief introduction to that and how to formulate it, the objectives with related to hypothesis. I need to clear on that part also, how this null hypothesis, chi-square test, and whatever has been mentioned in the course, it is very much uh, as per my
useful actually.
thesis related topic only. So that's the reason I'm incorporating this coursework.
Okay, nice. Actually, it is an introductory course. In this course, actually, there is probability theory, statistical inference, and correlation coefficients. These all are discussing here. Just an introductory part, and
Oh, yeah.
you can then continue with yourself after that. Okay. Anyone also who wants to introduce himself or herself? Okay. I think then we should start. Okay. Okay. In first week lectures, actually, we let's have a recap. for all the topics that are covered in the first week lectures. Okay, these are some of the topics that are covered. Like first, a sample space or a universal set is denoted by S. Okay, universal set everyone know actually. All the set theory laws are like in set theory. Set, what is a set actually? It is a collection of well-defined objects. Na? Collection of well-defined objects. Okay, and all the laws that uses that we use in set theory that also applicable in the probability theory. Okay, this is the same kind of universal set that we have already studied in set theory. A class is defined as the set of sets. Okay, and the collection is a set of classes. These are actually the terminology that may be used in the successive PPTs. Okay, now we have also learned about the rings and fields. A ring is defined as a non-empty class. Here it is a class. This is this class. Okay, a ring is defined as a non-empty class R. It is denoted by R of subset of S, which is a universal set. Means R is a subset of S. Is said to be a ring if these two conditions are satisfied. First one is the if AB belongs to R, then A union B also belongs to R. And if AB belongs to R implies A difference B also belongs to R. That is the finite union and difference. If these two are belongs to, then their union and difference are also belongs to the same set, then it is a ring. Okay. And in case of field, which is also known as algebra, okay, it is defined as the non-empty class F of subset S is said to be a field if AB belongs to F implies A union B belongs to F. That is same finite union. Okay, and if A belongs to F, then the complement of A also belongs to F. Okay, if A belongs to F, then its complement, that is S minus A, okay, also belongs to F. This is actually the definition only. Okay, the sir has already covered in a very vast way. Okay, now sigma ring and sigma field. Actually, sigma ring is a kind of ring in which the difference condition is satisfied, and for if AIs are the subsets, then union of AI or countably many unions, it also belongs to R. Then that ring is known as sigma ring. Okay, so we have concluded that the sigma ring also a ring. Every sigma ring is ring. Okay, and in the similar manner, sigma field or sigma algebra, it is also a non-empty class of F of subset S, and here countably many unions belongs to F if AI belongs to F. Then it is a sigma field or sigma algebra. And A belongs to A implies A complement belongs to F. Okay. Now our introductory part. Okay. So introduction to probability. Actually, probability is. Can anyone know about the definition of probability, or how can we understand about the probability? Anyone? Okay. Uh, Probability is actually the chance. Okay, it is a chance that any event or any situation occurs, or any event like any kind of thing that occurs have a possibility, have a chance to occur. Like it may rain or it may not. Okay, it is possible. So there are two types of probability, like subjective probability and like that we have run going to discuss objective probability, you may say. Okay, in subjective probability, like everyone have a different values. They have a kind of same sense, like it is possible that tomorrow there is the weather is around 10 degrees Celsius. Actually, I'm currently in Patna, so here the temperature is around 20 below currently now. It may possible. Okay, but in objective probability, uh, it is defined on the basis of some laws, some assumptions. Okay. So before discussing about the probability or definition of probabilities, we will first going to discuss about the some terminologies that are used in this, like experiments, random experiments, outcomes, sample space, events. Okay, these are the terms that we are oftenly using probability during the study of probability theory. Okay, so experiment is conducting something in certain condition which results in some outcomes. Okay, so anything that we do have certain outcomes. So that may be a kind of experiment. In probability, where there are two kinds of, maybe we can say that there are two kinds of experiments, like deterministic and random. A deterministic means certain, fixed. Like when we toss a biased coin, like a coin that has a both have head or tail faces, then it's sure that it always comes head. Okay. Yes, I think anyone wants to ask something. Pradeep. Okay, I can't hear you, Pradeep. Okay, if anyone have any doubt, they may ask. Okay, you may interrupt me in between. Okay, now deterministic and random experiments. Okay, what is a deterministic? Deterministic means that is fixed. When the experiment which have only one outcome, okay, that is a we are 100% sure that when we perform this, we get this. Then it is a deterministic. There is no randomness involved in that type of experiment. Like experiment related to physics or chemistry. Like suppose if we throw a ball in air, we are 100% sure it will fall back. Okay. In chemistry, when we react oxygen and hydrogen forms hydro water. I mean, if two molecules of H2 means H2 and O, then it's form H2O. Okay, under certain assumptions like certain temperature, certain pressure, certain volume. These are already in probability theory. We have always have assumptions. Okay. Now random experiment. Random experiment is something we are going to deal. Okay, like in random experiment, although we may fix the condition under which the trials are conducted, but the outcomes are still uncertain. Like we may fix the situation, but again, we are not 100% sure that what will going to happen or what is the observation we will get as an outcome. Okay, like in tossing a coin, in throwing a die, okay, drawing a card from a deck of cards. Okay, these are actually random experiments. We always use like tossing a coin, and we will know that either head comes or tail comes, but we are not sure whether under under the particular trial it comes either head or tail. We are no hundred. It is not 100% sure that always head comes or after head there is a tail comes. Okay, then this is a random experiment actually. Okay, and also like the terminologies that we will discuss, like outcomes, sample space, events, mutually exclusive and disjoint events, exhaustive events, independence events. These are terms we are oftenly used actually. Okay, so anyone want to say about anything regarding these terms, like outcomes? What is an outcome? We should interact actually, na? Yes.
Out
Hello, sir. Outcome means it is the
Yeah.
result of an experiment.
Yeah. Okay. Like exactly possible results of an experiment. Like when we perform like
If we
a
toss
die.
a coin,
Yes.
if we toss a coin, the outcomes are either head or tail.
Cell.
The results
Okay.
are
This is
called
the
outcome.
outcome. Yes. And what is a sample space then?
Set of all outcomes are called
Yes.
sample
All the
space.
possible outcomes. Then we collect that as a set. We form a
Yes.
set. of all possible outcome, and this is called the sample space. And in probability, our first aim is to find out the what is the sample space in the particular problem. So our more than half work has been done there, because in probability our in like in successive we have seen like in denominator part there is a sample space related quantity, like the number of object or number of entries or number of units that are present in sample space. That is our motto. So in each and every problem related to probability, our first aim is to uh, find out the what is the sample space. Okay, and then what is an event? Event is actually a subset of sample space. Event is a subset of sample space. Like anything, subset may be the whole sample space. Subset may be none, like void sets, or maybe some set, some proper subset. Okay, like when we when we like toss two coins, for example, when we saw toss two coins simultaneously, then the possibility is that like when we toss two coins, then we get either head head or head tail or tail head or tail tail. These are the possible outcomes. No other outcomes are observed during the tossing two coins. Okay, and when we say what is the probability, or we say that the event E is defined as the getting one head, one head. Okay, then this is the event. We see that the E is defined E in roster form. When we write the set as a roster form, then E is what? It's HT or TH. Okay, so this is the there is number of head is one. So we already see that E is nothing but the subset of the sample space S. Here we see that E subset S. So it is a subset of S or sample space. Okay. Now there are different kinds of events actually. Okay, like equally likely events that I am just here actually because a question related to that, but equally likely events. Okay, so those events that have the same chance or same probability is known as equally likely events. Okay, like while performing a rolling a die, while tossing a coin, the chances of occurring head and getting tail is equal. While rolling a die, the chances of getting an even number is equal to the chances of getting an odd number. So these are the equally likely events. Suppose we are rolling a die, for example. Okay, these are the sample space. Okay, so A is getting even number and B is getting odd number. So probability, actually, we will going to discuss later, but the probability, or we can say that the number of observation in the number of elements in A is actually 2, 4, and 6, and in B we get 1, 3, and 5. Since there is a total of 6 outcomes here, and 3 belongs to A and 3 belongs to B, so it is equally probable, na? It is equally likely that either the chances of occurring A, event A, and the chance of occurring B both are same. So this is called equally likely events. So event A and event B are equally likely. Okay, mutually exclusive events, it is also known as disjoint events. Okay, disjoint means there is no common in between A and B, in between the events. Like here, for the same example, if A is even and B is odd number, so here we have seen that A intersection B, which is equal to pi, because there is nothing common in between A and B. So it is disjoint as well. The event A and event B are disjoint. Yeah, or we have also called it mutually exclusive. There is nothing in between common in between. Okay. So exhaustive events. Exhaustive events are set of those events that covers the entire sample space. That means here again we have considered the same example, like rolling a die. A is getting even and B is getting odd number. So when we take the union of these events, here we have only two events. When we have taking the union of these events, we get nothing but sample space. Then it is called as exhaustive events. So event A and B are mutually exclusive events. Event A and B are also exhaustive events, and it is also equally likely events. Okay, and now independent events. What is independent event? Anyone can define independent events. Okay, independent, like the occurrence of one event is not going to affect the occurrence of another event, then it is said to be independent event. Okay, suppose we roll a die, okay, and getting head, sorry, not get, actually getting 1, getting 2, getting 3, 4, 5 and 6, all are independent. Na? Suppose in first trial we get 4 after rolling a die, and in second trial we get 5, or we get 4, or we get 3. The, the outcome in the second trial does not have depend on the first trial. So this is independent from the trial. Okay. So this is called the independent event. Okay. When two or more than two events are not related, kind of, we can say. And for checking the independency of two events, suppose again we have two events A and B. Okay. Then event A. Wait. Okay. For checking purpose of two events are said to be independent. If two events A and B, these are said to be independent if A intersection B can be written as probability of A into probability of B. When this condition holds, then it is said to be independent events. Okay, this is the necessary and sufficient condition for two or more than two events is said to be independent. Okay, now we come at the classical definition of probability. How many definitions are there? Anyone know? I think
Basically,
you
there are
people have
two or
learned
three definitions, sir. Hello?
four times. Yes, yes.
Hello?
Yes, I can hear you. Can you hear us?
Sir. One is relative frequency definition,
Okay.
and another is some random variable. Using random variable, we can define using our
Okay.
probability function,
Sir, I think there is one
distribution function.
empirical one
Uh,
definition is there. Empirical frequency.
Sir,
yes, yes, yes.
relative frequency means when n tends to infinity,
Yes, yes.
number of trial tends to infinity, then
Yes.
our number of favorable cases divided by our total number of cases, you can say.
Total number of cases. Yes, yes. Okay. And Gauss, what are you saying?
Sir, I heard something like empirical frequency is also a classical definition of this.
Yes, yes. So there are two, according to you. I mean,
I don't know, but I heard. But
okay, okay. Actually, there are three definitions of probability till now. Okay. You may work on the fourth
okay.
one. Okay. But there are exactly three definitions of probability. Actually, Satya. Okay. Satya has said the right thing. The relative definition is also known as the empirical definition. Actually, both are same. Okay, we will going to learn this. Like there are three definitions. The first one is given by Laplace in 1812, and that is the classical definition. This is also called mathematical definition as well. Okay, and this is the very simple definition. Uh, like when we have we have conducted a random experiment, and the outcomes had n outcomes. A total of n outcomes are there. Okay, and there are n outcomes. Okay, then the probability of any event can be find out or can be calculated with the help of this formula: number of favorable cases or total number of cases. Okay, but there are some conditions, there are some assumptions. In statistics, there always have some assumptions. When we are going to discuss about the density function, anything, there is some assumptions. Okay, so here, what are the assumptions? Like the events that must be mutually exclusive, that we have learned, that is disjoint. Okay, that are exhaustive events and that are equally likely events. In that case, we use classical definition of probability to calculate any kind of events that are defined there. Okay, suppose here a total observation are or total outcomes are n, and m is our favorable number of outcomes, that is favorable to n. Okay, so we evaluate the probability like m by n. This is the simple probability, like classical probability. It gives the weight actually, weight or chance of occurrence. Like in 5,000 times, 777 times this thing happen, or 57 times this thing happen. This is this kind of probability, simple. Okay, and this is the base for the probability definition. Okay, here we see that there are various properties of probabilities actually. Like any event E, so the probability of that event always greater than, probability of any event E always greater than or equal to 0. Also, probability of any event E is all less than or equal to 1. Suppose from here we have seen that probability of any event is 0. Then what can we say about this? Anyone
Empty event
can?
Sir,
Empty.
can you
empty
Okay.
come
event
again?
or pass, you can say null event.
Yes.
No
Possible
event
event.
has occurred.
Okay. I can't actually hear clearly.
No event has
Actually,
occurred.
this is, yes. No event has occurred. Then this event is known as impossible event. These are impossible events. Okay. The event that have a 0 probability, that is impossible event. And in a similar manner, probability of E equal to 1. This type event is called anyone?
Sure event.
Sure event.
Okay, okay, sure, exactly. This is called sure or certain events.
Sure event.
Sure events. Okay. Also, okay. Any other property? Anyone recall? Like if probability of any event is, suppose P, this implies probability of E complement, or we can also write E complement like this, equal to what?
1 minus
1 minus
probability of
probability of
E.
Exactly, 1 minus probability of A. Correct. Okay. So event and the complement both are actually disjoint, and the union of event any subset and its complement equal to sample space, that same property or same law satisfy here. The probability of any event E and the probability of the complement of that event, then the sum of these both equals 1. Okay, but here are drawbacks of these definition. Like n needs to be finite. The first drawback is n needs to be finite. If total number of exhaustive cases are infinite, then in each and every cases we get the 0 as a probability. But this is not the correct. So this is the drawback of the classical definition. Also, assumptions of equally likely events. In case we don't have equally likely events, then this definition is not valid. Then because this definition is created on the base of these assumptions: mutually exclusive, exhaustive, and equally likely. Okay, so these are the drawbacks of this definition. Actually, sir has already taught these things, but this is my first class. So we will going to discuss some basic topics. Okay. Now the second was is statistical or empirical definition. That is also called relative definition. That I think Satya has told the same thing. Okay. Okay. In this, if the trial is infinitely large, in that case we take the limit. Okay. Here I think this should be small n. Okay. Small n tends to infinity. Okay. So the event E or the probability of event E is defined as the limit. We have taken the limit of the same favorable cases and total cases. This is the probability. Now it also have some limitations actually. Like first, it may possible that limit may not attain always the first possibilities. Or second one is that if an experiment is repeated a large number of times, the experimental condition may not remain identical and homogeneous, because in this definition the situation must be identical or homogeneous throughout the trial or throughout the experiment. It is the very basic assumption in all probability theory that the event on which we perform the experiment, that should be identical throughout the experiment. Okay, so it is not very like it is not possible actually, na? So these are the drawback or limitation of the statistical or empirical definition. And the third definition, that is called axiomatic definition. This is the best we have got yet. Okay, in this definition, we have some assumptions, like some properties has to be followed. Here we have, like we see that if S is a sample space, it is a finite sample space, and A be an event in S. Okay, a finite is stand for means countable. Okay, and A be an event in S. Okay, then in this approach, the probability of event event A, is a real number assigned to A which satisfy the following three axioms. And what are those axioms? The first one is the probability must lie within 0 to 1. Okay, this is the non-negativity property. The second one is the probability of the sample space is 1. And the third one is if A1, A2 up to a countable sequence of mutually exclusive. We should focus here. Mutually exclusive events. Okay, like A1 intersection A2 equal to 5 and all. A1 या AI AJ कर लेते हैं. Sorry, AI and AJ equal to 5. Okay, then in that case, the probability of the union of AI is equal to the summation of the probability of AI. Sorry for this print here, probability of AI. Okay, these are the three axioms or three properties that should be followed. So we calculate the probability of A, any event A. Okay, these are the three definitions. And now we come at inequality part. Can anyone tell the what is inequality or why inequality is used? Anyone? We have used
Sorry,
different type of inequality. Yes, yes.
yes, sir. Inequality is used to compare the things, sir, when they are associated with real numbers, sir.
Sir, I think it is a relation between the two expressions.
Okay. Anyone else? No. Okay. Actually, we see here that it is either greater than or less than symbol already there. Na? Inequality, there should be always greater than or equal to or less than or equal to. That means the value, for example, the value of x is 4 or greater than 4. What we means, what we conclude here, like the value of x, for x belongs to some natural number, then x is 4 or 5 or 6 or this. So it is a bound, no? It is a kind of bound. So inequality actually gives us kind of bounds. either it is a lower bound or it is an upper bound. Okay, inequality gives us a bound. Okay, so we have two kinds of inequality here, like Boole's inequalities and Bonferroni's inequality. Okay, and these two inequalities are kind of similar actually. Okay, like for first, we have A1, A2, A3 up to n events. Okay, and n events are maybe disjoint or may not be disjoint, but we have only information about that there are n events. Okay, so a probability of union of AI is less than or equal to summation of probability of AI. We have seen here, na, like here, the third axioms of axiomatic definition equal to this. And here we see that the probability of union of AI is less than or equal to. In axiomatic, we see that the probability of union of AI equal to summation of probability of AI. And here we say that it is less than or equal to, because it may possible that the events are mutually exclusive or disjoint. In case of disjoint events, this inequality converts to equality. That is the third exam of the axiomatic definition. Okay, so the maximum value of probability of union of AI must be equal to the sum of the individual probabilities of events. Maximum value. Either that is equal to that or that must be less than or that. These values. Okay. Here, if AI, I have already written a remark, AI and AJ are disjoint sets, then the inequality becomes an equality. Okay. Now the next one is Bonferroni inequality. This inequality, again the same, it gives the bound. Actually, the Boole's inequality gives the one-sided bound. Like union of AI must be less than or equal to this. That is the maximum bound, upper bound for union of AI. But here we have a union of AI, have a lower bound and upper bound as well. Both. We have a both. Like from here, this part is actually what? Boole's inequality. Okay. And this part also here, which gives the lower bound or lower probability for the probability of union of AI. Okay. This is for the lower bound and this is for the upper bound. So it gives a bound. Okay. Okay. Anyone wants to ask anything till now, or any topics that they have learned during the lectures? They may ask. Or now, from now onwards, we are going to discuss about the numericals actually. Okay. Anyone wants to ask anything? Okay, then let's start with. Okay, the first question is like, let A equals 0, A, 0, 1 be a non-empty subset of R, where R denotes the set of real numbers. It is a set of real numbers. Then which of the following is a sigma algebra? Okay, sigma algebra. First, we should recall the definition of sigma algebra. Sigma algebra is what? It has two properties, na? Like for AI belongs to F. F is a sigma algebra. Or then union of AI also belongs to F. And the second one is, if A belongs to F, implies A complement belongs to F. Okay, these two properties should be satisfied for A to be a sigma algebra. Okay, now check option A. We have start from option A. Here we are given phi, 0 and A. Suppose we have taken A1 which is an element or subset of this, subset of this term, subset of this A1. Okay, this. And when we take complement of A1, this is equal to what? Can anyone tell? The subset of this. Sorry, the complement of this. It's 1, na? Because there are only two elements, na? A. In A, there are only two elements. In A, there are only two elements, 0 and 1. So when we consider 0, because 0 belongs to A, so complement of 0, that is 1. It also belongs to A. But here, for example, for option 1, A does not belong to for option A. This implies it is incorrect or wrong. The second one is, suppose for B option, we have taken again in the similar manner, like A2, which is equal to 1. So this implies A2 complement, which is equal to 0, does not belongs to A. Actually, I should write here like something E1, E2, E3, E4. So let me correct them. E1, this is E2. Okay. So this implies option 2 is also wrong. We will consider option 4 first, because option 3 is the right one actually. For option 2, again here we see that 0 and 1 are there. Okay, so obvious 0 and 1 are there. But what about the other terms? Like if 0 are there and 1 is there. What about the union term? This is actually 0, 1, which is equal to A, which not belongs to E4. It should be 4. That means option D is also the incorrect one. So option C is the right one. Here we can check that if we had consider 5, then complement of 5 is A, which is there. If we are considering 0, 1 is there. If we are considering 1, 0 is there. And if we are considering A, then its complement 5 is there. So this property holds. Also, we also check the union property. So consider any two elements in option C, like 0 and 5. It comes out to be 0. 0 and 1. It comes out to be 0 and 1, which is equal to A. A union any member of this, it gives A. So each and every condition, this condition also follows. So option C is the right one. Okay.
Gupta sir,
Yes.
whatever this solved one, can we get a copy of it, or it will be shared something to all the students?
Okay. Actually, we are
Why
instructed
we are
to
not
share
noting,
this.
we are not noting down now. If you want, we can note down, start noting down. If we get a copy of it, then we will only see how it is coming, the
No, no.
results.
Actually, I am instructed to submit this with the lectures. So you will get both things. Okay. Or you people have already
fair enough.
enrolled. Na? So you people get both things. Or in case if you are not able to find this, you may contact me. Okay. Actually, this lecture is also uploaded on YouTube, and I will share my email ID as well. Okay. So you people directly contact me. Okay.
No, why? Because we are not noting down. Only we are seeing
Yeah,
how the
no
results are.
problem. No problem. Just try to understand first. Our only motto is this now. Try to
Fair enough.
understand. Okay. Yes. Everything will be provided. Okay. Now from question number 1, actually from here onward, we are going to discuss about the questions related to probability. Okay. Actually, one thing that I learn or I understand that probability is actually logic. how much you logically think. It's only about this. And you may play
Sir,
with numbers. Yes.
can you please tell me
Hello.
the exact difference between A and A complement?
I clearly can't understand. Can you repeat once?
A and A complement, what is the difference exactly?
Okay. A and
Okay.
A complement.
Yes, yes.
Okay. Okay. I can show with the help of any sets actually. Okay. I can write here for with the help of different color of pen. Wait. Like suppose for example we are considering like rolling a die, then we will get 1 2 3 4 5 and 6, and we define any event A, any event, suppose A. We can define event multiple ways, in a multiple ways, like getting a multiple of 3, getting a multiple of 4, getting an even number, getting an odd number, getting a prime number. These all are the events associated with this sample space. Okay. So suppose I can write like this. Getting multiple of 3. Okay. So what? If we write this set as a in roster form, what we get?
3 comma 6.
3 comma 6. So A complement is sample space, that is universal set minus set event. What it gives? 1 2 4 5. Can you understand?
Yes, sir.
Yeah, complement actually it is also property na, from here, like okay, I haven't have a space here, but I can write here actually.
That means you have to subtract the total set of events from A elements.
Yes, actually your voice is not clearly audible for me, so yeah, either you repeat or let me complete. Let me complete first. Okay, like we can see there, we can say like here in above we learn about the probability, like probability of any event is suppose 1 minus probability of E complement. This is the same is this, because probability of sample space is 1, probability of any event, suppose we have considered it P, then probability of E complement plus probability of E equal to 1. This implies probability of any event equal to 1 minus probability of E complement. This is the same this, like this. We have actually applied the P in this condition. Complement. Complement is, you people are familiar with Venn diagram, na?
Yes, sir.
Yes, sir.
Yeah. Suppose this is a universal set or S. We denote S or U. Okay, and this is a any event or any set A. This one. Okay, then what is the complement of A? This is again this one. So this is the same thing, na? The set, the complement of A S minus, that means like a universal set minus that particular event or the particular set. Event is actually a set, na? So this one. Okay. Now understand this or let or not?
Yes, sir. I understand.
Okay then. Okay. Ask anything, whatever you want. Okay, because it's for us also, for me also to learn something. If I don't know the answer, I will definitely look into it. Okay, now we will start with the questions. Okay, from question 1. Here we are given A equals n square minus 1, where n belongs to the natural number and n is less than 4. And B is the set defined B such that B is an odd number. This B is less than 10. Okay, you know that na, there are the representation of set. We can write set in two forms. Na? The first one is set builder form, and the second one is roster form. Are you people familiar with it?
Sir, we are not.
Yes, sir.
Okay.
I am
Yes.
not.
Okay. Let me. Actually, this is a kind of rule, and in roster form, we write down the set as its element with the help of its elements. Like here, the A and B are given in roster form. Okay. Sorry, in set builder form. It gives a formula. It gives a rule to build the set. Okay. Okay. Arya, I think you should mute yourself.
चाय बेटा चाय बेटा
Arya,
yes, sir.
I think you should mute yourself actually. Okay. Okay. In roster form, we write the element of that regarding this. Like here, what is A? Can anyone tell what elements are there in A?
A is equal to 0, 3, and 8, sir.
0, 3, and 8. And how it
Yes.
comes?
Yeah, we substitute
Everyone?
the value of
Yes.
n.
We substitute the value of n, which is 1, 2, and 3.
1, 2, and
Okay.
3, sir.
N equal to 1, 2, and 3. And for that, we get small a, which is equal to 1 square minus 1, which is equal to 0. 1 is square, second, 2 square minus 1, which is equal to 3. And 3 square minus 1, which is equal to 8. So these are the set builder form. And this is the roster form of the representation of set. Okay. Now, set B can also be written in roster form as? Can anyone tell?
Yeah, set B is equal to 1, 3, 5, 7, and 9, sir.
1, 3, 5, 7, and 9. Because this is a strictly less than. Na? So any odd number that is less than 12, sorry, less than 10. And n is a natural number first. So 1, from 1, we start 1, 3, 5, 7, and 9. Okay. So we have now A and B. Now, what is the question? The question is then which of the following is correct? Okay. So actually here everything is in, what is this? This symbol is called?
Intersection.
Intersection, exactly. Means those elements that are common in both the sets. Okay. So here A intersection B is like 0, 3, 8, intersection 1, 3, 5, 7, and 9. And we get
3.
3 as an intersection. Okay. So which option is correct? A.
Third option. Sir.
Option A.
Sorry, third. C.
Okay. Third, option C. Na? Option C is the right one. This implies option C. Okay. It's a very simple question actually. This is a set question actually. This is a question related to set theory. Like A union B, A intersection B, A difference B. These all are used in set theory. And we use the same laws, same theory in probability. Just like you people also learn about this, na? Know about this actually. Like number of elements in A union B equal to number of element in A plus number of element in B minus number of elements in A intersection B. For set theory, you people definitely read this thing. If anyone not, then this is the case, or I can show, or I can try to explain how it comes. If anyone wants to know, everyone know about this, na?
Yeah, sir, please. I am very poor in statistics. Please help.
Okay, no problem. Okay, like let's try to visualize this thing. Okay, because proving is not possible here. Suppose it's A, it's B. Set A, set B, and this square is a universal set. Okay, so here we can see that like suppose here we element A is there, element B. Okay, I actually Okay, try to understand. And here C is there. Okay, so in A, there are A plus B elements. In B, there are B plus C element. And in A union B, there are A plus B plus C. And A intersection B, there are B. Okay, so here we see that when we add A plus B, then we write A plus B and plus B plus C, which is equal to A plus B plus C plus B, which is equal to, actually this is just for playing purpose, nothing is A union B minus B. So from there this comes out, na? Because this B element repeated, it counted twice in A also and in B also. So when we add these two things, one time we minus this as well, which is common in between. In A and B, small b is common element. So we should also subtract this element because it is common. Okay, we counted it twice in this set, A union B. And A union B is defined as either A or B. Okay, A union B is either A or B. And in set theory, we should write the elements only once. Okay. Okay. Can you understand?
Yes, sir. Yes, sir.
Okay. It's a very simple thing. Actually, try. Okay. Just try to visualize things. The first lecture or the first year is actually overall logical thing. If you don't know, just try to visualize what is this. Okay. Here you see that na, A and in A and B, B is counted twice. So we need to subtract it one time. So this is common portion and subtracted this for one time. And again, here we see that if we replace N with P, probability of A union B equals probability of A plus probability of B minus probability of A intersection B. This is the additive formula for probability theory. Okay, what we do? We replace N with P. Same. All the set theory rules and laws are used in probability theory. Okay, there is no change. The same. Okay, now second question. Actually, we have many questions, so let's start. Okay, now second question. A ball drawn at random from a box containing 6 red balls, 4 white balls, and 5 blue balls. Suppose we have a box like this. We have a 6 red balls, 4 white balls, and 5 blue balls. Okay. So the question is determine the probability that it is a red ball. What is the probability that when we draw randomly without looking into the box a ball, it should be red? And then what is the chances? So first, suppose R defines the getting a red ball. Okay. Getting a red ball. Okay. When we randomly draw one ball and it is a red ball. So our next aim is to number of elements. Okay. And what is this? It is 6 because it is in favor of. Na? Getting a red ball is in my favor or our favor. Okay. And the number of red ball is 6. So any of these 6, when we remove one ball, it is in favor of us. And the total number of balls is 6 plus 4 plus 5, which is equal to 15. And the probability of getting a red ball is what? Number of red balls, which is in our favor, and the total number of balls, which is equal to 6 upon 15. We can simplify this with 2 by 5. Okay. Or we can say that 40% chance. Okay, so suppose we are playing a game like in this, we need to draw a red ball. So there are 40% chance that a red ball is drawn when we randomly draw a ball. Okay. This is the answer. Okay. If anyone have any query regarding the questions, they may ask. Okay. Otherwise, we will continue. Okay. Now, question number third. Find the probability of 4 turning up at least once in 2 tosses of a fair coin. Okay. Here there should be dice. DIE. Actually, die is used for singular and dice is for plural. Since we have a 1, so it is a die. Okay. 4 turning up. Okay. Now, S1. Suppose we have a die and we roll. We will get either 1, 1. It's not 1, 1. Sorry. Either 1 or 2 or 3 or 4 or 5 or 6. Okay. And when we again tosses the die, we will get either 1 or 2 or 3 or 4 or 5 or 6. So we have 2 possibilities. Like in throwing the die twice, we get either 1 1 or 1 2 or 1 3 or 1 4 or 1 5 or 1 6. So our sample space looks like this actually. In first row we get 1 and in second row we get 1. In first row we get 1 and in second row we get 2. In first row we get 3, 1 and in second row we get 3 and so on, 1 and 6. Okay. So how many possible outcomes are there? Can anyone tell me?
36.
36. Okay. And how you got the answer? How can you say that? Na? There are 36 elements. Actually, here you can see that when we roll a die, the possible outcomes is 6. Okay. And the number of times we roll or the number of dice we consider, we take the power of that number. Okay. Here we throw twice. So 6 square that equal to 36. So there are total 36 outcomes are there. And you may visualize that how this you may visualize like how the outcomes are there, like 1 1 1 2 1 3 so on, 2 2 2 2 1 2 2 so on, and this. Okay. Now our again.
Sir, I
Yes.
I thought 6 into 5 into 4 into 3 into 1, 720 times I thought in that way to may also come.
No. Actually, in that way, how if you have any confusion, just try to first draw, and then you have an image of that. Na? That's why I have write this actually for this purpose only. S1, S2. 1 is related to 1, 2, 3, 4, 5, and 6. Again, 2 also relates in the similar manner. 3 also relate in the similar manner. So there are 6 with 6. 6 into 6 equals 36. Suppose, for example, suppose we have considering 4 dice or 3 dice. Then what? It is 6 to the power 4. Because every S1 has 1 to 6, S2 has 1 to 6, S3 has 1 to 6, and S4 has 1 to 6. Okay. So 1 1 like 1 1 1 1, then 1 1 1 2. In the similar manner, 1 1 1 6. Okay. Then 1 1 2 1. Okay. Then we will change this one. Then we will change this one. Then we will change this one. It is a power, 2 to the power. Okay. Anyone also want to ask anything?
So got it. Thank you.
Okay. Now our aim is to find out the 4 turning up at least once. Okay. So we need to write this. Look, how many times we get 4? Like 1 4 in first column, it's 1 4. First row 1 4, then it's 2 4, then it's 3 4, then it's 4 4, then it's 5 4, then it's 6 4, and then what? It's 4 1, it's 4 2, it's 4 3. It's 4 4.
Sir, 4 4 already came, no?
Yes, yes. That's why I've written that with the different color, no?
Mm-hmm.
4 6. Is there any other possibilities? Actually, you may see that, no, like it goes out like this and this. 4 column in fourth, like this and like this. So it repeated twice. Okay, it repeated 2 times. So we remove this. So there are first there are 6 columns, 6 rows. So 6 plus 6 equals 12. But since it repeat it here there is an intersection point, na, which apply which lie on this line and this line as well, both. So we remove it for one, like here, na. Actually, that's why I have written here B. It is common and it includes in A and B both. Again, this 4 4 lie in row and in column wise. When we count column wise, then also 4 4, then row wise also 4 4, then we minus 1. So 12 minus 1 equal to 11. So number of elements in A equals 11, and total number of elements we will denote with n, 36. Then what is the probability? It's number of elements in A upon number of elements in S, which is equal to 11 upon 36. Is it okay? Okay, next question. Let probability of A is this, like, and probability of B, and probability of A complement intersection B complement is this, and we need to evaluate probability of A union B complement. So can anyone tell me how to proceed? Okay. First, we need to know about the De Morgan's law, actually, for here. It states like this, suppose probability of A complement intersection B complement equal to probability of A union B complement. Okay, the intersection converted into union, and the complement that apply on both A and B is now apply on the union. Okay, this is the De Morgan's law. This may also written as A union B complement. Okay, A complement union B complement equal to probability of A intersection B complement. Okay, this is the De Morgan's law. So we use this law. Okay, so first we are given like probability of A complement intersection B complement is 1 by 3. Okay, so here it's 1 by 3 equal to, we can write this probability of A intersection B complement can be written is 1 minus probability of A intersection B. Can we write this?
Yes, sir. Yes, sir.
Yes. Okay. Then from there we calculate 1 minus probability of A intersection B. And from here we have found that probability of A intersection B is what? It's 2 by 3.
So that there is some mistake.
Where?
So 1 by 3 is equal to probability of A complement intersection B complement. But here you write probability of A complement
Okay,
union A
okay,
complement.
okay. Yes, yes, got it, got it, got it. Thank you, thank you. Okay, let me erase this. We will start again. Okay. The rules are right. There is no issue actually. Actually, we are given this quantity, na? We are given this quantity, na? A complement intersection B complement means 1 by 3. So this value is given 1 by 3. Okay. And this can be written as this. On this can be written 1 minus probability of A union B. Can we write this? Anyone?
Yes, sir.
Yes, sir. Yes,
Yes.
sir.
Yes, okay. Okay, now from here, probability of A union B equals 2 by 3. Okay, from here, we will get probability of A union B equals 2 by 3. Now, from A union B, we need to calculate A intersection B because we want to calculate A union B complement. So, what we can calculate with the help of additive law, like probability of A union B equals probability of A plus probability of B minus probability of A intersection B. Okay, from here 2 by 3 equals probability of A 1 by 2 plus probability of B 1 by 2 minus probability of A intersection B. And from here we calculate probability of A intersection B equals it's 1 minus 2 by 3 which is equal to 1 by 3. Okay, so we have calculated probability of A union B and probability of A intersection B. Now what? Again, we need to calculate probability of this. Okay, so probability of A union B complement. This can be written as probability of A plus probability of B complement minus probability of A intersection B complement. Can we write like this? This is A union
Yes.
B complement. A union B, na? Okay. Also, we have this probability. So we can write this as probability of A intersection B complement can be written as probability of A minus probability of A intersection B. Anyone have any problem? Okay. So we can write this in this form. So probability of A union B complement can be written as probability of A plus probability of B complement minus probability of A plus probability of A intersection B from here. So probability of A getting cancelled out. Okay, and after solving, we will get A union B complement equals what? Probability of B complement, which is equal to 1 by 2, plus probability of A intersection B, which is equal to 1 by 3. So it's 5 by 6. Anyone have any doubts? Okay. Now, question number 5. Here, two dices are rolled by two players A and B. A throws 10. What is the probability that B throws more than A? Okay. We need to visualize. Like here, A rolls 10. Okay. So B need to rolls more than 12. More than A means either 11 or 12. Here, two dices are rolled. Okay. I think there is something. Anyone wants to ask anything? Okay. Here, when we roll two die, the sum on the top of both the dice are vary from 2 to 12, and this is the sum on both die. Sum on both dice. Okay. So if A gets 10 and B needs more than A, then the favorable condition for B is 11 or 12. So what is the sample space? It's 1 1, it's 1 2, it's 1 3, it's 1 4, 1 5, 1 6, 2 1. I'm going to write the whole 36 elements. So once I write, please click an image in your mind. 2 2, 2 3, 2 4, 2 5, 2 6, 3 1, 3 2, 3 3, 4, 3 6, 4 1, and 5 1, 5 4, and the last is 6 1, 6 2, 6 3, 6 4, 6 5, and 6 6. Okay, these are the total outcomes when we roll two dice. Okay, when we roll one die twice or when we roll two dice simultaneously, both have the same outcome, and this is the outcome. Okay, now what? A B wants 11 or 12. So the sum on 11 and 12 can be visualized here like this, like 11 or 12. Okay, so it's 11, it's 11, it's 12. So there are three possibilities for B. B in favor of B, there are only three possible outcomes like 5 6, 6 5, and the last is 6 6. Okay, so the next is probability that B throw more than A equals number of elements in B and the number of elements in S, which is equal to 3 upon 36. This is equal to 1 by 12. Is it okay? Anyone?
Yeah.
Okay. Okay, thank you. Okay, now we are going to discuss about the cards. Everyone know about the distribution of cards? Is there
No, sir.
anyone?
No, sir, I don't.
You don't know? You don't know.
No.
Okay. Actually, okay. I think okay. I'll first introduce about the distribution of cards. Okay. So a deck of card. Suppose when we are saying a deck of cards, it has 52 cards. Okay. In 52 cards, it is divided on two different types, and it is based on colors. Okay. So there are 26 red cards and 26 black cards. I'm talking about the standard cards. There may different type of color, but normally red and black cards are there. Okay. And then the 26 red cards are divided into two parts. And similar manner, 26 black cards are also divided into two parts. Okay. So it based on designs like suits बोलते हैं. That is also called suits. ठीक है. Okay. And this is okay. This one is diamond. This is called diamond. This is called heart. This is called clubs. And this is called spades. Okay, there are four types of design of designs on the cards. The red one are diamond and heart, and the black one are clubs and spades. Okay, all have 13 cards. 13 diamonds are there, 13 hearts are there, 13 clubs are there, and 13 spades are there. Okay, and the whole 13 cards, there are different like symbols, not symbols actually, there are digits or alphabets are there. So from 2 to 3, 4 up to 10, there are numbers written on each card. Okay, in out of 13 card, one card has written 2, one has on written 3, one has 4, 5, and 10. So there are 9 cards, and there are still 4 cards. That is Jack, Queen, King, and Ace. So this is 4 cards, and total 13 cards are distributed in this manner. Okay, the same manner apply in heart, clubs, and spades. Can you understand the
Sir, got it.
distribution of cards? Got it?
Yeah, yeah,
Okay.
thank you.
Yes. Also, you can also see here that there are a total alphabetical cards and numerical cards. Suppose I am asking you, Acha, okay. How many cards are there in a deck of cards on which A is written?
Four.
Number of, yes,
Four.
4 exactly. There are 4 cards, and each card has a different shape. Like one has a diamond of ace of diamond, one has an ace of heart, clubs, and spades. There are one of each. Okay, this is the distribution of standard card. Okay, so my question is like this, a rapid question. Okay, so how many alphabetical cards are there in a deck of cards?
Four, sir.
Anyone?
16.
Four,
16.
4.
4 into, yes, exactly, 4 into 4, that equals alpha.
16.
Okay, sorry. Alphabetical cards are 16 and numerical cards are 9 into 4, that equals 36. Okay, and the total card is 52. Also one more terms are used here, like face card. Anyone heard about face card?
JQKA are the face
JQ
cards.
JQKA.
No, sir. Only J, Q, and K.
J, Q, and K, exactly. Only J, Q, and K have faces on the card. Okay. So only J, Q, K are known as face cards. So
Sir,
total number of face cards, yes.
what is JQKA?
Its A is stand for ace,
Okay, sir.
and J is stand for Jack, Q for queen, and K for king. There are 4
Got it, sir.
alphabetical cards. Okay, and on these alphabetical cards, this Jack, Queen, and King have a face, have a whole picture on the card actually. Okay, so this is called face card, and there is a total of 12 face cards are there. Okay, so there's a lot of question. We can create lot of question regarding cards. Like, what is the problem? Suppose let's first solve this question, then we will discuss about the different cards problem. Like, from a pack of 52 cards, 2 cards are drawn at random. Okay, we need to draw 2 cards. What is the probability that one is ace and the other is king? So how to proceed? Look, see, like we have a total number of king cards. Anyone? How many king cards are there in a deck of 52 cards?
4,
Four.
king and K.
Exactly,
4.
4. and we need to draw one ace and one king. Okay, so what is the possibility that 4c1 for king and 4c1 for ace? Actually, there are four possibilities. Like suppose a person A draw ace of diamond. Okay, and the second person draw ace of clubs. So that's why there are four possibilities. So 4c1 possibilities to draw ace and 4c1 possibilities to draw king. And what is the possibility to draw two cards from a deck of 52 cards?
15c2.
Exactly. Total possibilities 15c2. Okay, so the probability of getting one ace and one king is 4c1 into 4c1 or whole divided by 52c2. Anyone have any problem? Is it understandable or not? Is it clear now how to solve the card problem?
Yes, sir.
Okay.
Yes,
And
sir. Yes,
what,
understood, sir.
okay. A rapid question kind of like suppose we draw a random card from a deck of cards. Okay. So what is the probability that it has a spades? It has spades.
1 by
Anyone?
4, sir.
It's 1 by 13 upon 52. Exactly. 1 by 4. What is the possibility that it is queen?
1 by 13, sir. 4 by
1 by
52.
Okay. Yes. Or what is the probability of getting a face card?
12 by 52, sir.
Exactly. In a similar manner, only you need to know about the distribution of cards, and the rest you will solve. You need to memorize how many cards are there and how many cards are this type. So you may solve this. Okay. Now next is in tossing 3 coins at a time, what is the probability of getting at most one head? Okay, it's a very simple question actually. So first is the sample is what is the sample space for this? And the number of elements in sample space. The first question is what is the number of sample space? What is the number? 8, exactly. How? Because when we toss a coin, there are two possibilities, and we toss 3 coins. That means 2 to the power 3, that is 8. Okay. So let me write the sample space first. So we get head, head, head. First coin, second coin, third coin. Okay. Head, head, head. Head, head, tail. H, T, H, H, T, T. In a similar fashion, we can write like T, H, H, T, H, T, 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 H, and the last one is T, T, T. These are the only 8 possibilities. There is no ninth one. Okay, when we toss 3 coins. Okay, now the question is, what is the probability of getting at most one head? Okay, you should focus on at most and at least. So at most one head means suppose A is an event defined as getting at most one head. Okay, so getting at most one head. So the probability is, so first we write down the what, which one comes here. Okay, which elements come here from sample space? Can anyone?
2 by 8 or 1 by 4.
Okay. Actually, you got the answer, but I'm still in the set in favor of A. Which element should come in favor of A? Anyone?
H, 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 H,
What?
H, H, H.
H, H, H.
Yes.
Are you sure? Actually, it is at most one head, na? Either there is no
HT,
head or
HT
there
and TH.
okay, let me write then. HHT. Is it right?
No,
No, exactly.
HT and
Because there
TH.
is yes, yes. HTH. HTT. Then THT. And the last one is anyone? At most one head, na? Like either one head or there is no head. That means there is tail also, na?
TTT.
Yes, yes, TTT, exactly. There are four possibilities. H. Okay, there is one mistake. And where it is?
TT.
This one.
Uh,
Yes, yes, this
TTH.
one also. It's TTH. Okay. So these there are these four. Number of elements in A is 4. So the probability of A is what? Number of elements in A upon number of elements is A. This is equal to 4 by 8,
1
which
upon 2.
equals 1 by 2. Okay. Now next question. So here, what is the probability that in a group of 4 persons, no two have birthday on the same weekday? Means no 2 person have a birthday on the same day. Like if so, there are 4 persons. Suppose it's a very logical question. Like suppose there are 4 people, A, B, C, and D. Okay. So our first question is: it may possible that any person have birthday on any day, na? Like any 7 possible day, na? So first, the number of sample space or the total possible outcomes is what? Anyone? Okay. Okay. See here. Look, like person A has 7 day total possibility. I am talking about the total possibility. Person A has a birthday on any of the 7 days, na? And similarly for person B also, for person C also, and person D also. So 7 to the power 4, the total number of possibility that the 4 person have birthdays, either same days or different days. Okay. Now again, we need to uh, define that no 2 person have the birthday on the same days. Okay. Suppose in this case, A has a birthday on any on the 7 days. Okay. Okay. Am I audible now?
Yes, sir. Yes, sir.
Okay. Okay. Suppose person A has a birthday on any of the 7 days, because there are still all 7 days are available for him. And when A has a birthday on some specific day, how many possibilities for B? Can
6.
anyone tell? 6, exactly. And what about the C?
5.
5, sir.
5 and 4. So the total favorable cases are 7 into 6 into 5 into 4. So now the probability is what? Like 7 into 6 into 5 into 4, and whole divided by 7 to the power 4.
Four.
Is it clear? Okay. Now this question. Okay. And how to solve this question?
4-digit numbers are found selecting random results out of
4-digit number. Like we have a number, a 4-digit number. Okay. Uh, formed and selecting randomly digit of 0. We have we have 0, 1, 2, 3, 4, 5. Total 6 numbers are there. Okay. And we need to form 4-digit number without repetition. Okay, without repetition. So what is the probability that the number is divisible by 5? Okay. So anyone can tell me what is the property that a number is divisible by 5 or not? How can we check?
Sir, last number should be either 0 or 5.
Exactly. The unit place should be either 0 or 5. Okay. So, and also, if we are talking about the 4-digit number, then that means at first digit, there should be other than 0 number. Like we can't start with the 0, na? Like if we are writing 1, 2, 3, it is a 3-digit number, na? It is not a 4-digit number. Okay. So for a 4-digit number, the starting number should be non-zero. Okay. So our aim is to find the total possibilities and favorable possibilities. Okay. So total in this current scenario, total possible number, how many numbers are generated from the number of given these 6 numbers? Okay. Suppose this is the first number, second, third, fourth. Okay. The same concept that we have used in previous question. Same. So how many possibilities are there for first digit? Anyone?
Only 3.
Only 3.
One. Sorry,
Five.
only 4. 1, 2, 3, 4.
1, 2, 3, 4. Are you sure?
5, sir.
5. Exactly. Okay. I am talking about the total, not about the divisible by 5 first. And the second one?
4.
5. It's still 5 because 0 can be here. Na? We can write 0 here, but not here. For first place, we have 1, 2, 3, 4, or 5 as a possibility. But for second place, we have 0, 1, 2, 3, and some out of these, 1 is written here, and the rest 4 are remaining, and 0 and the rest 4 is 5. Okay. And then 4 and then 3. This comes out to be 300. So from these numbers, we can construct 300. Okay, I think Ritesh, please mute yourself.
हमारे भाग भाग के कॉलेज रे डेफिनेटली लेट पहुंचे कोई था ही नहीं क्लास में हम सब कुछ चेक किए मैम भी लीव पे नहीं है बच्चों को भी कोई नहीं है किसी कुछ मैसेज नहीं है
Ritesh.
तो हम आधे घंटे बैठे रहे
Okay. Hello. Anyone hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the total possibilities are 300. Means we can construct 300 different numbers without repetition from the given digits. Okay. Now we are going to talk about the favorable outcomes. How many numbers are in our favor? That means how many numbers are divisible by 5. Okay. First of all, for divisible with 5, what should be here at fourth place or at unit place? How many numbers are
0
there?
and 4.
0 and
0 and 5.
5.
2.
Exactly. So there are only 2 possibilities for this. And what about these 3? Can anyone tell me? It's a simple logical, na? Just try. How many? Like for first, suppose for this place, we have 1, 2, 3, and 4. So 4. For second place, how many numbers are there?
5, sir.
5.
Yeah, 0 we need to consider for second place. No?
Yes, you may consider, but we have already considered here either 0 or 5, na?
Okay.
So 1 is fixed there. So 1 is left. That means here also we have
4.
only 4 possibilities for there, and here 3. So this comes out to be. Is it? Am I right? Okay. I think there is something Is it correct or not? Anyone?
Yes, sir. Yes, sir. It is 96. Correct.
93? Okay. Okay. Now the probability that 4-digit number are formed selecting randomly out of these three is what? It's 96 upon
96 by 300.
you can solve, and it's 40. Okay, 24 na? 4. Okay, no, 8 upon 25. Okay, I think there is something mistake. Can anyone tell me?
Yeah, sir. The second number is 5, it seems.
Yes. Actually, we should consider about two. Let me erase this. Actually, there is something wrong. Okay, we should consider two possibilities. No? Like actually, for here, unit place if 0 appears and unit place 5 appears. Okay, then we get the right choice, right number of cases. Suppose 0 are here. So from these three, how many possibilities are there? Now it is clearly. Anyone tell?
For first position, 4.
4. Are you sure?
Why? Because we have already
Because
removed
5,
0
5,
are there, no?
5,
0 is here.
5,
So all
sir.
the
5,
5
5.
possibilities are there, 4 are there, 3 are there, and this has 1 possibilities. So it comes out to be 5 into 4 into 3. That comes out to be 60. And for this, it is 4, it
4.
is 4, it is 3. And it has 1 possibilities, not 5. Because 5 is there. That means 1 possibilities. So it comes out to be 48. So total 4-digit number form is 108. And the probability is 108 divided by 300, which comes out to be, I think, 9 upon 25. Okay. Is it clear?
Yes, sir.
Actually, we should actually divide. Na? Like there are two possibilities, but 0 and 5 are there. When it comes out to be 0, then what are the cases is different because the number 0 is included here. Na? That's why. Okay, now next question. Like 5 pairs of husband and wife attended a concert and sit randomly in a row. What is the probability that each would sit together? Okay, there are 5 couples actually. Okay, so first couple, second couple, third, fourth, and fifth. Okay, what is the probability that each would sit together? Suppose 10 person. There are 10 person. Na? There are 10 person, and 10 person is the 10 person is sit in 10 factorial ways. So this is clear, na? Total possible ways. Total possible ways, how many? Because there are 10 persons, so 10 factorial ways are possible. I think this is clear for everyone. Hello.
Yes, sir. Tell.
Is it clear? No? Okay. So it is clear that 10 factorial ways are there to sit 10%. Now the restriction is all each would sit together. All the couples should sit together. So first thing, we treated those couple as a single unit. Okay. So when we treated them as a single unit, then it comes out to be there are total 5 couples, 5 persons. So favorable case, there are 5 factorial ways first. And again, since these two, suppose this one is male and this one is man or woman. Okay, so it may also possible that na, like first woman and then men. Is it possible?
Yes, sir.
Yes.
So 2 factorial times. And how many couples are there? 5. 1, 2, 3, 4, 5.
5.
So 2 factorial to the power 5. This is also there. So this is in our favorable case. This is the total number of possible outcomes when each couple should sit together, because it is not mentioned that no who sit right or next. Anyone can sit any side. So this is our favorable case. Is it clear?
Yes, sir.
Okay, then again the probability is what? Favorable case, like 5 factorial, 2 factorial to the power 5, and the whole divided by 10 factorial. Okay, you may solve this. It is a very large number. Okay, it comes out to be 1 upon 945 actually, when you solve this. Okay, now next question is like, hello.
Yes, sir.
Okay, anyone have any question? What? Okay, let's start then. Here again, probability of A equals 1 by 3, probability of B equals 3 by 4, and probability of A union B equals this. We need to find probability of A intersection B and A complement intersection B complement. Better? Okay, now first probability of A union B equals probability of A plus probability of B minus probability of A intersection B. Okay, from here we say that it's 11 upon 12 equals 1 upon 3 plus 3 upon 4 minus probability of A intersection B. So probability of A intersection B is what? 12, 4 plus 9. It's 13 minus 11 upon 12. This comes out to be 1 by 6. It is simple calculation. You may solve. Okay. We include this formula. We are given this, and this values. We can solve this for. Also, the probability of A complement intersection B complement equals. Here we use De Morgan's law. Can we use it or not?
Yes, sir.
Okay. And with the help of De Morgan's law, we can write the like probability of not intersection. It is already given. A union B complement.
Complement.
And A union B complement is what? Is nothing but 1 minus probability of A union. And it's 1 minus A union B is 11 upon 12. This comes out to be 1 by 12. Is it clear? It's a simple question based on formula actually. Okay. Okay, now this is a question. Classical probability is if possible, if outcomes are. We are talking about the classical probability. So which option is correct? A, B, C, or D? Can anyone tell me?
C, sir.
It should be C. Okay. According to you, it's C. And what about others? Anyone have other options correct?
50.
C. Okay. Anyone else? Listen, if people don't understand, then ask. Okay.
All
It's
are
very simple.
correct.
Like in class, yes. It, like in equally likely events, in classical probability, the event should be equally likely outcomes are there. So first one is correct. Mutually exclusive is correct. Unequally likely, obviously, either one is correct or third option is correct. So third is not correct, and exhaustive. So option C is the right one. It is clear. Option C. Okay. Again, one of the requirement of the statistical definition of probability is that the experiment is repeated a large number of times under the same set of conditions. we are talking about the statistical definition, that is empirical definition. So it is correct or not? The number of possible outcomes of an experiment is very large. The outcomes of an experiment are equally likely, and there is at least one outcome of an experiment favoring the given event. Can anyone tell me?
One, sir.
Which one is correct and why? Actually, you may see that, na? Like there is at least one outcome of an experiment favoring the given event. No, this is not the case. Na? We have studied about the statistical definition, and we are not talking about this assumption or this property. Again, the outcomes of an experiment are equally likely. No, this is the case for classical definition. So it is not. And the third one is the number of possible outcomes of an experiment is very large. The number of possible outcomes of an experiment is very large, and the first one is the experiment is repeated a large number of times under the same set of conditions. If you people recall, this is the drawback of statistical. That means this is the correct one. And this is not the correct, because it says the number of possible outcomes of an experiment is very large. No, it should not. It may or it may not. Okay, so option 1 is the correct one. Okay. Is it clear? Hello?
Sir, clear. Got it.
Yeah, okay, thank you. Okay. Now, there are two groups of students consisting 4 boys and 2 girls, and 3 boys and 4 girls. Okay, there are group 1. Okay, sorry. There are group 1 which have 4 boys and 2 girls, and there is group 2 which has 3 boys and 1 girl. One student is selected from both the groups. What is the probability that 1 boy and 1 girl will be selected? Okay, can anyone tell me how? Here we see that in group 1 there are 6 students, and in group 2 there are 4 students. Okay, and our aim is to one student is selected from both groups. Can anyone tell me? Am I audible or not?
Sir, you're audible.
Yes, sir, audible.
Okay. Can anyone tell me then? What are the cases or what are the possibilities, or how can I proceed in this case? Here it is clear, na? Like, sorry, it is clear, na? One student is selected from both the group. What is the probability that 1 boy and 1 girl is selected? So in first case, suppose first case, we are talking about 1 boy and 1 girl is selected. So what is the probability of selecting boy? Okay, let me write then something like probability as 1 boy and 1 girl. Okay. So probability that 1 boy from group 1 and 1 girl from group 2, either this case, or 1 boy from group 2 and 1 girl from group 1. This case. Is it the only case possible? Na? Because we need to select 1 boy and 1 girl from both groups. So either the boy comes from group 1 or from 2, and similarly the girls. Is it clear or not? Is it simply you can understand? If anyone has any doubt, please ask. Or it is a simple question actually. Let's see. 1 boy. selecting a boy from group 1. What are the possibilities? There are 4 boys and total number of students is 6. So 4 by 6 multiplied by 1 girl from group 2. It's 1 by 4.
4 by
Yes?
4 by 7.
True.
4 by 7.
True.
Total 7 students.
Okay,
Group
I
1.
can't hear what you are telling.
Total number of students is 7 in group 1. 4 by 6.
In group 1. Okay. I think 4 boys and 2 girls are there in group 1, na? So
Sorry,
there are
group
6. Okay, no problem. Okay. Okay, 4 by 6 into 1 by 4. And again, from one boy is selected from group 2. That means boy is selected from group 2. That means 3 by 4. And girl is selected from group 1. That is 2 by 6. So it comes out to be 1 by 6 plus it comes out to be 1 by 4. And this is the case. Like 2, it comes out to be 12. 2 plus 3, which is equal to 5 by 12 is the answer. Anyone have any problem? We can divide this now. Like we need to select one boy and one girl. We can select from any of the group now, like from group 1 or from group 2. So we consider both the possibilities. A boy consider from group 1 and then consider from group 2, and similarly for girls. Okay. Now next question is the probability of Mr. R living 20 years more is 1 by 5. That of Mr. S is 1 by 7. Okay. Then what is the probability that at least one of them will survive 20 years? Okay. And how can we proceed for this? Anyone? Like suppose we can write the event like this, na? Suppose R, Mr. R survived for 20 years. Survive for 20 years. And similarly survive for 20 years. Okay. So we are given that probability that R will survive for 20 years is 1 by 5. And probability that the person S or Mr. S will survive is 1 by 7. Okay. And we need to calculate that any one of them. So if R survive, S do not survive, or if R do not survive, S survive, na? This is the case, na? Can you understand this? Here it is clearly mentioned that no, at least one of them will survive. Plus R and S both survive. Here R survive, S not survive. Person R do not survive for 20 years, but S survive, and here both the person will survive for 20 years. And we have the probability of all the thing, na? Like what? Person R will survive 1 by 5, person S will not survive 6 by 7, because the probability of survival for person S is 1 by 7. Then the probability for not survival is 1 minus 1 by 7, which is equal to 6 by 7. Similarly, for R, it's 4 by 5 into it's 1 by 7, and plus for both it's 1 by 5 plus it's 1 by 7. Is it clear or not? If not, I will solve this with another approach.
Clear, sir. Clear.
1 minus,
Clear?
sir, second is
Another
1
Yeah,
minus
exactly.
5.
Yes, yes. Second approach is probability, sorry, not it's a 1 minus probability of none will survive. So none will survive means 1 minus probability of R is not survive and S is not survive. 1 minus R survival is 1 by 5, it's 4 by 5, and S is not survive is 6 by 7. And now you may solve this. It's 1 minus 24 upon 35. This comes out to be 11 upon 35. And from here also we will get 11 upon 35 if you solve this. Okay. Okay. Again, we have an unbiased coin tossed for 4 times. Okay. The number of possible outcomes. Can anyone tell?
16.
16. Exactly. So number of sample space is 2 to the power 4, that equal to 16. And the outcomes are like this actually. Head, 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 tail, and so on up to tail, 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 and tail. There are 60 outcomes are there. Okay. And the question is then, what is the probability that the number of heads exceeds the number of tails? Suppose number of head is 0, the number of tail is more than 0. What is the probability that the number of head exceeds the number of tails? Means number of head should be exceeded the number of tail. So here the possible number of head is 0, 1, 2, 3, and 4. And for similarly 4, 3, 1, sorry, 4, 3, 2, 1, 0. This is number of heads and this is number of tails. And you may then solve this. Na? Is it simple to solve this question again now? Na? Like here, suppose A is what? A is what? Head exceeds the number of tails. So what are the outcomes? Head exceeds the number of
3
tails.
and 4.
The
3
first
and
one
4.
is 3 and 4. Like first one is this, head exceeds, then head, tail. Head, tail, head. Head, tail, head. T, H, H. And is there any other possibilities that number of head is more than the number of tail? No, there is no any possibility other than this, na? Because now when we write, for example, when we write like HHTT, then it's equal number, na? So it is not the case. So probability that head exceeds the number of tail is, it's 5 upon 16. Is it clear?
Yes, sir.
Okay. I
Sir,
think 2 or 3
second
more
method, can we
questions are
solve
there.
this by
We will solve
binomial
this.
distribution?
Or
Binomial distribution.
what? I can't hear you
Binomial.
exactly. Please.
We can solve it by binomial distribution for x is 0 or 1, sir.
Exactly. But actually, this is not till in our syllabus. Na? It will,
Okay,
we
okay,
will
okay.
learn about this in second or third. That's why I have not solved this. All this probability
Okay.
can be solved with the help of any distribution actually.
Yeah, yes,
Okay.
sir. Yes.
We will learn about how to solve, then we will try to figure out which distribution is used here. Like here, it is used by with the help of binomial. Exactly. You can solve. Okay. Now equation 17. Okay, here we see that let A and B be two events such that probability of A union B equals 3 by 4 and probability of okay, it's greater than or equal to 3 by 4 and this is this. Statement 1 and statement 2 are given. The probability of A plus B is greater than or equal to 7 by 8 and A plus B is less than or equal to 11 by 8. Okay, choose the correct option. Can you people solve this? Anyone who can? Okay, let me, because we are dealing with A union B, A intersection B, A and B. So what? Probability of A union B is what? Is greater than 3 by 4. This implies probability of A plus probability of B minus probability of A intersection B is greater than or equal to 3 by 4. Is it given? So this
Yes.
implies probability of A plus probability of B is what? Greater than or equal to 3 by 4 minus its plus probability of this. Okay. Now we have some bounds for this here. Okay. So what if we take the value is 1 by 8, greater than or equal to 1 by 8? Here we see that it is greater than or equal to 1 by 8. So when we put it's 1 by 8, this implies probability of A plus probability of B is greater than or equal to 3 by 4 plus 1 by 8. That equals 9 by 8. So not 9, it's 7 by 8, no, not 9 by 8. 3 or 4. 6 to 8. Okay, 3 by 4 plus 6, sorry, 7 by 8. So probability of A plus probability of B is 7 by 8. That means statement 1 is correct. Okay, and now we put the value again. And we got, okay, 3 by 8 and plus the maximum value of this is what? Like here in the same case, the maximum value of this is what?
By 8.
Maximum value of A union B.
3 by 8.
Like we can write 3 by 8. 3 by 8. How?
Yes, 3 by 8.
Like probability of A plus probability of B, it can be written like from here itself. Okay. Let me write clearly. Okay. Like probability of A plus probability of B minus probability of A intersection B is what? Probability of A union B. It is the formula. From here, we write probability of A plus probability of B is probability of A union B minus probability of A intersection B. Okay. Now probability of A union B is what? 3 by 4. So when we increase the value, either 3 by 4 or more than 3 by 4, that means this can be written like this. Okay, I think something else. Okay. Let me check the solution. I have already done it quickly. Okay, 3 by 4. Okay, from here actually, probability of A intersection B is less than or equal to 3 by 8 when we consider this, and probability of A union B is less than or equal to 1.
Sir,
Yes.
yeah,
Yes.
probability of A union B plus probability of A intersection B.
Okay. Yes. This minus comes here as a plus. Okay. It is correct. Okay. Now, how to proceed then? Anyone tell me? Probability of A plus probability of B. So A intersection B and A union B. So this comes out to be 1 plus, and this value is less than or equal to 3 by 8. And because we consider the maximum value of this, so it is less than or equal to consider. So from here we see that it's 11 by 8. Wait, let me. From here, Again, let's see. Probability of A union B is like this. Okay. So probability of A plus probability of B equal to probability of A union B plus probability of A intersection B. Now we consider the maximum value of this, because the maximum value of probability of A union B is 1, and the maximum value of probability of A intersection B is 3 by 8 as given in our question. Okay, so we consider, so this equality sign now less than or converted into less than or equal to. So probability of A plus probability of B is now less than or equal to 3 by 8, because we need to calculate the bound, and it is given in statement number 2. So both the statements are
Both are true.
trues. Exactly. There are 3 more questions actually: 18, 19, and 20. So should I complete it, or it's for your homework kind of thing?
Complete it, sir.
Complete. Okay, okay, good. Okay, I have actually solution, but there. Okay, now in question 18, suppose that 6 good bulbs and 20 defective bulbs have been mixed up. 6 good bulbs and 2 defective bulbs are mixed up. Defective bulbs. To find the good bulbs, we test them to buy one at random without replacement. One by one at random without replacement. What is the probability that both of the defective bulbs are in first 2 tests? Since when we start testing in first test and in second test, we get the defective bulbs. Okay, this is the case actually. So what is the possibilities? Can anyone tell me how to proceed? Am I audible or not?
Yes, sir, you are audible.
Okay, okay, okay. Just try to think actually how to proceed first. We have total bulbs. How many bulbs are there? That equals to 8. So we need to find the both defective bulbs in first 2 tests. See, like we need to find both defective bulbs in first 2 tests. Both defective bulbs in first 2 tests. Means when we draw first out of 8, how many in favor? How many defective bulbs are there? It's 2
2
bulbs
by
are there,
8.
na? Exactly, 2 by 8. And because here it is clearly mentioned without replacement, then now in
Then
the second round
1 by
there is
7.
a total of 1 by exactly 7 bulbs are there, and as in first draw we have drawn 1 defective bulb, then the last one is there. So it comes out to be 1 upon 28. 1 upon 28. Exactly. Is it clear? Okay. Now question number 19. In a city, 30% of the people read Hindi newspaper. Okay. And 20% of the people read English newspaper. And 10% both. If a person at random, if a person selected at random, then what is the probability he or she English or Hindi? Okay. Suppose H is stand for the person read Hindi newspaper, and E for he or she read English newspaper. Okay. Then those who read both E intersection H, both newspaper. Okay. So probability of H is given as 0.3, 30% of this. Probability of E given as 20%, 0.2. and probability that the person read Hindi and English both newspaper is 0.1. We need to ask Hindi or English. That is probability that Hindi or English is stand for union. When we are dealing with and in set theory, we are talking about the union. And when they are okay, it's a mistake. It's intersection. And when we are dealing with or, it's about union. So here or, that means H intersection U, and this can be written as H E okay, sorry. Probability of H, that is equal to 0.3. Probability of E 0.2 minus 0.1. This comes out to be 0.5. Means 50% of the people read any kind of newspaper.
4.
Okay. Yes.
Sir, 0.4.
4 होगा सर, point 4.
अरे okay. Yes. Sorry. It's 0.4. It's 5 minus 4. Okay. Now the last question. From integer 1 to 40, both inclusive. Like our sample space is like this: 1, 2, up to 39, 40. One integer is chosen at random. What is the probability that it is divisible by 4 or 5? Again, like A, event A is defined as the number is divisible by 4, and B is as the number is divisible by 5. Which number is divisible by 4? From 1 to 40, it's 4, 8, 12,
10.
16, 20, yes, exactly, 24, 28, 32, 36, and 40. Okay. And what about the 5? 5, 10, 15, 20, 25, 30, 35, and 40. Okay. Now what is A intersection B? It comes out to be 20 and 40, na? Is it correct? So probability of getting A is number of elements in A or total number of elements. So this is 10 upon 40, which is equal to 1 by 4. Again, number of elements in B equals number of elements, sorry, it's probability of B equals, and number total, this comes out to be 8. 8 upon 40, that's equals to 1 by 5. And probability of A intersection B is what? 2 upon 40, that equals 1 upon 20. Is it correct up to this point?
Yes, sir.
Okay. Now, like probability that we were asking about the OR, means probability of A union B. Again, it's probability of A plus probability of B minus probability of A intersection B. And this comes out to be 1 by 4 plus 1 by 5 minus 1 by 20. Then it's 20, it's 5 plus 4 minus 1, which is equal to 8 upon 20, which can simplify as 2 upon 5. Is it clear?
Yes, sir.
Is it clear? Yes. So anyone have any doubts regarding today's lecture or want to ask anything about me? Then he or she may ask. Okay.
No, sir.
Then first let me. Okay. First, let me stop the recording.